All right, so this is information on the chemistry of life. Ask Mr. Tolles to please fast forward to where your particular class left off. Take notes in Cornell Notes. And let's be clear, some of these questions, some of this content will be on the exam on next week. So let's go through this. Again, fast forward where you need to. If you don't watch this in class, you'll have it at home. I will post it this evening with the message that you shouldn't watch it until after class. Mr. Tolles may not be able to get it to work with his login, so sometimes YouTube isn't allowed unless you have the full teacher access. All right, so the chemistry of life is organic chemistry, and it is focused on this one element type called carbon. Now, that's going to be an important element, as you'll see throughout the course. Carbon has 6 protons and has mass of 12, and we'll discuss how to calculate atomic mass and to discover the neutron number in just a little bit. All right. So an element is a substance that can't be broken down into simpler chemical substances. So what's that mean? Well, I don't like that they use plutonium, but we should point out that plutonium is radioactive. It is an example of an element, and oxygen is an example of another element. And there's many different elements on the periodic table, which is a summary of all the known elements in the world, in the universe. And so when we take a look at something like water, which is H2O, it looks like this. This is what it looks like. And I like water because most kids have heard of H2O. And that's 2 particular elements, the element oxygen, the element hydrogen. And there's 2 hydrogens. That's what this little 2 at this little subscript 2 means. So H2O means that you have 2 hydrogens and 1 oxygen. This is what that looks like. The 2 hydrogens are each bonded to the oxygen, and we'll talk about what bonding is. But we could take this water, and we can break it up into 2 different elements. Can you guess what those 2 elements are? That's right. It would be oxygen and hydrogen. Now, there are 2 hydrogens there, but the 2 elements that water can be broken down to is oxygen and hydrogen. You cannot break oxygen down any further. Although this was water, it was a compound, it's a molecular compound, water can be broken down into 2 elements, one being, of course, oxygen and the other hydrogen. So those are the 2 elements. As we said, there's 2 hydrogens, and there's only 1 oxygen, but the point is that there's an element called hydrogen and an element called oxygen, and that's what makes water up. So you can take water and break it down into these 2 elements, where oxygen and hydrogen are those elements because you can't break them down any further. So life on Earth is composed of many different elements, but one common group of elements that compose every living cell on the planet, and I don't care if it's a tree or if it's a human or bacteria, are these elements here. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Phosphorus phosphorus here is misspelled. So it should be another H there. So phosphorus and sulfur. Each of these is a different element that each individual element cannot be broken down any further, and each element has its own qualities. So carbon has atomic number 6 and a mass number of 12, rounding. Here's the hydrogen with atomic number of 1 and a mass number of 1, again rounding. And oxygen, each of these are different elements that make up this schnapps, if you will. So each of these elements make up the main components of a living system or living cell. You need to know what these are for the exam. So I'm letting you know that this is extremely important. I will put it on the exam. Okay, moving on. So an atom is made up of different components. A nucleus of an atom is made up of both positive and negative, or rather positive and neutral charges. And so you have a positive charge for a proton and a neutral charge for a neutron. And that's what's in the nucleus. Now, again, I don't like this word nucleus because some kids get confused when you use nucleus here in chemistry or in the beginning of the chemistry of life. And then when we look at a cell, we're going to have an organelle that's called the nucleus and nucleolus, and it has all kinds of different organelles in it. And these little organelles and membranes, where this one here is also called the nucleus. Don't confuse the two, okay? One's the nucleus of a cell, the other's the nucleus of an atom. The nucleus of an atom has both protons and neutrons. There they are, protons and neutrons. Protons have a positive charge, neutrons a zero charge. So try to remember that. People confuse this all the time. I've seen kids put electron when they meant to put protons, and the kids knew better. But when they get on the test, for some reason, they tend to confuse the two. There's no need to confuse them if you keep them straight. Put them on your index cards or when you recite them in class to each other or during advisory. Make sure you know the difference between proton, neutron, and electron. It's also on your practice sheets today. So atomic number is equal to the number of protons, and that's also equal to the electrons when the atom is neutral. That means no charge. So protons have a positive charge. Electrons have a negative charge. All right, an atomic number is the number of protons. That literally that's what that means. So when you hear atomic number, it's just simply the number of protons. So that's why these two are equal. These two are always true. These two are always true. Proton number, atomic number are the same thing. Where this one is true only, or rather, I shouldn't have drawn it that way. These two are true only when the atom is neutral. And why does that make sense? Because if you have an atom and it has this bunch of electrons going around it, and this has 6 protons. How do you get a neutral atom? That means it has zero charge. If it didn't have any electrons, if they just had protons and neutrons are neutral, so we don't have to worry about those. They have no charge. If this has 6 pluses, how many negatives do you need to get 0? Well, hopefully you said 6. So 6 minus 6 is 0, and that is why this is true only when the protons equals the electron number, only when the atom is neutral. All right. Okay, so what's key here is that the atomic mass, and I'm going to go ahead and put mass number, atomic mass, is equal to protons, let me not put a plus, protons plus neutrons. All right. So if I give you the mass number and I tell you it's 12, and I tell you the proton number, I tell you it's carbon, so it's you can look it up on the periodic table, but it's 6 plus 6. And of course, this is the mass number is rounding off. How many neutrons do I have? Well, this is just a simple application of algebra. So how do I get the neutron number by itself? I subtract 6 from both sides, and that equals 6 equals the number of neutrons. So the number of neutrons is equal to number 6. That is that is the simplest form of the problem. But can you please pay attention to this? If I ask you for the number of neutrons, that was easy. If I ask you for the proton number and I give you the number of neutrons and the mass number, you should be able to find that. If I give you a number of protons and neutrons, you should be able to find the mass number. So really, the formula is pretty straightforward. There shouldn't be any issues. And by the way, this is what kind of the example that they have here in the slideshow. So you should be able to calculate the mass number, the proton number, or the neutron number pretty easily. This should be a gimme question if you remember that mass equals protons plus neutrons. All right, so isotopes are different forms of the same element. So what does that mean? Well, an element is defined by the atomic number. The atomic number defines the element. So if I tell you it's atomic number 6, that equals carbon. If I tell you it's atomic number 8, that equals oxygen. Atomic number 1 is equal to hydrogen. And atomic number 2 is equal to helium. And there's just a ton of them, all right? So if you have an atomic number that defines the element, it turns out, and remembering that when you have a number of protons, let's say you have carbon has 6 protons, there they are. But then normally carbon has a mass of 12, so this is carbon. This is carbon 12, and let me change that. Carbon 12. But then you could also have carbon 14, and that goes back to isotopic decay, or carbon dating. It's called carbon dating. So here we can put neutron, N for neutron. So that's 6 neutrons, 6 protons. That's carbon. We're not dealing with electrons right now. We'll deal with electrons in the next slide. But if you have carbon that has 6 neutrons and 6 protons, we call that carbon 12. That's the stable form. That's the most stable form. We find most of the carbon in the universe is carbon 12. But there is this carbon that's a little unstable, which means it decays, it's radioactive. And this carbon has 1, 2, 3, 4, 5, 6. Why does it have 6? How do I know it has 6 protons? Because it's carbon. So carbon has to have 6 protons because the atomic number defines the element. So 6 protons. So that's how many neutrons then? So that means that if you have 6 protons still, and you know you have atomic mass of 14, remembering that atomic mass equals protons plus neutrons. I have the number of protons at 6, atomic mass is 14. How many neutrons do I have? That equals 8. So I have 8 neutrons. Or protons and neutrons together equal 8. All right, so when we're dealing with an unstable element, this is unstable. There's less of it, so we call this the isotope. But they're actually isotopes of each other. So they're both carbon. They're both carbon. One's carbon 12 and one's carbon 14. They're different forms of the same element, so we call them isotopes. All right, so that's isotopes, and you can see how you can calculate protons and neutrons. Let's move on. Compound. A compound is a substance that is composed of atoms of two or more different elements chemically combined. So here's an example, 3 carbons, and we have something here called 3 carbons, 5 hydrogens, and 2 oxygens. So 2 or more different elements chemically combined. And another example is H2O. Water is also a compound. Ethanol. Ethanol is and so ethanol actually has this many atoms and this many different elements. Now here's a question for you. How many different elements are in water? Well, I hope you said 2 elements. One meaning one oxygen, or oxygen is one of the elements, and the other element's hydrogen. Well, how many elements are involved in ethanol? Ethanol is an alcohol. Well, hopefully you say 3, and that's equal to carbon, hydrogen, and oxygen. All right. So the number of elements involved in a number of different kinds of atoms is not the same as the number of atoms. If you look here, how many atoms are involved? There's only 2 elements in water, but there's 1, 2, 3 atoms. So there's 3 atoms and 2 elements. Here in ethanol, you have only 3 elements, but you have 1 plus 3 is 4, plus 1 is 5, plus 2 is 7, plus another one is 8, and the last is 9. So there's actually 9 atoms that make up that molecule. There's 3 atoms that make up this molecule, and there's 3 elements in this molecule, and there's 2 elements in this molecule. So these are the molecules the atoms bonded together. Here I'm showing the bonds, and here I'm not. Okay, so that leads us to what are these things that we call bonds? Well, when we're talking about bonds, there are the electrons, remember, on the outside of the atom. And so if we take a look at oxygen, for instance, oxygen has 6 or 8 protons in the center. There's neutrons, but that's really not important for chemistry. It's important more for nuclear chemistry, not the kind of chemistry we need to worry about. And it turns out that this oxygen atom, O atom, can make 2 bonds. It can share 2 electrons. Usually I would try to explain this to you and go through the whole electron orbitals and try to explain why the atoms share electrons, but I'm going to tell you that for this class it's not that important. When you get into chemistry, they'll go through and talk about the different kinds of bonds that atoms can make. But what you can do is you can look at oxygen, and then you have hydrogen, and hydrogen can share 1 electron, and so it could either give away or share an electron. And oxygen can share an electron. And when these share electrons, they gather all the electrons they need. So by sharing, they get what they need. And they form this thing called a covalent bond. All right, so this is a covalent bond. Water is a molecule. It's covalently bonded together. There's another type of compound that's not really a molecule. It's an ionic compound. And what that means is that there's another thing that atoms do, and that's that they give away or take electrons. So if we take a look at another element called chlorine, a very highly electronegative, or let's just say a very strong atom, likes to pull electrons away. And it comes into contact with this thing called sodium. It's very weak electronegativity, or let's just say it likes to give away electrons. This has an electron to give, and this wants an electron, so really badly. The chlorine is much more powerful when it comes to grabbing electrons. And so what chlorine does is it takes the electron. When that happens, sodium now has one more proton than electron. It was neutral before, all right? It had 11 protons, 11 electrons, all right? Sodium is atomic number 11. And now that it lost an electron, it has 11 protons, and only 10 electrons. So electrons are negative and protons are positive. So that leaves you with a +1 charge. I hope that makes sense. So what happens is that sodium has a +1 charge. So it's sodium +1. Now when we take a look at chlorine, chlorine has an atomic number of 17. So it's 17 protons. And before it took an electron, it had 8, that's 17 pluses. It had 17 electrons before it took one. But then after it took one, you have chlorine with an extra electron. So now you have, oops, I put positive on both of those, didn't I? 17 positives and 17 negatives. And when you look at chlorine, it takes the 2 electrons. So now it has an extra electron, 2 extra electrons where sodium lost it. And if instead it has 17 protons minus 18 electrons. Why does it have 18 now? Because it used to have 17, it took one. So now it has a -1 charge. So chlorine has a -1 charge. Sodium has a +1, and chlorine has a -1. Well, what does what does a positive do to a negative? I hope you say they attract. So whenever the sodium is near the chlorine, they kind of stick together like magnets. They're not sharing electrons, so it's not as strong a bond as this covalent bond up here, okay? These two aren't really sharing electrons. They're just sticking near each other because they're opposite charges. So sodium chloride, or you know it as table salt, is sodium metal, and chlorine, the chlorine and sodium atom, bonding or being attracted to one another because of this ionic nature, or the fact that they're charged. These atoms are charged. Their protons and electrons are not equal to each other. All right, so when we're talking about chemical reactions, you have to remember that all living things are made of cells, and cells are bags. You know, they're lipid layers. They're three-dimensional. They're not just length and width. They actually have, you know, space. They're more like baggies than they are like a flat piece of paper. And here you have a nucleus. You have an endoplasmic reticulum. They have a rough. You have the smooth. You have a Golgi body. You have ribosomes. You have vesicles. You have kind of a matrix, etc. So you have cells, all right? And these cells, what they do is they conduct chemical reactions, okay? And these chemical reactions, they're just going on all the time, everywhere, all kinds of different chemical reactions. And that's what makes up life. That's everything that is life is all about chemical reactions. Now, the interesting thing is that chemical reactions require energy. Again, chemical reactions. And in fact, any action or reaction, right, requires energy. Okay, and the process of how many chemical reactions are positive or negative, building or taking apart, we call that metabolism. So chemical reactions require energy, and all the chemical reactions together in a system, any system. In this case, we're talking about, you know, like let's say your human body, or a cell, or an elephant, or a kangaroo, what have you. All the chemical reactions that occur within that organism, we call it metabolism. So that's the sum of all the reactions. So all the positive and negative reactions, I shouldn't say positive and negative because that might confuse you with the ions. So let's just say all the building and all the taking apart. So there's two things that living things can do. Just like if you think of living things as giant Lego builders, you can build something up, right? So you pile up the Legos one on top of the other, clicking them as you go, and build something. Or you can have something built already, and what you could do is just start taking them apart. So when you're building them up, we call that anabolism. That's where we get this word anabolic steroids. Those are steroids that help you build muscle, right? So that's anabolism. By the way, very bad for you. Don't take steroids unless the doctor prescribes them. They have a lot of side effects. So when a chemical reaction is building, we call it anabolism. So that's building up the body, building muscle, etc. So making complex molecules from simple ones, like Lego. If you think of a Lego as a simple molecule, but then you put a bunch of these together, you build something. So that's anabolism. Catabolism is when you have a complex molecule already, you have something built, and you're breaking it apart. You're breaking it down. So that's called catabolism. And you do both. You do both of these. All living things do both of these. And the sum of these two, the building and the breaking down, the sum is known as metabolism. So when they say you have a fast metabolism, or you have a slow metabolism, they're talking about how much in total, because energy is required for both of these, right? How much energy do you have? How much energy is being burnt up to either break things down or build things up? I say most people don't really have fast or slow metabolism. It's just some people move around a lot more, and others don't move around as much. All right, so if people say you have a fast metabolism, it's probably just that you do a lot. You're always constantly moving, and that's really breaking down sugars. It's building up muscle, so you end up staying thin. Where if you don't move around a lot, you're not moving and walking and constantly on the move for whatever reason, then you're not really tearing down or building up much of anything, so your metabolism is slower. There are ways to speed up your metabolism by diet or exercise. Those are the healthiest ways for you to speed up your metabolism. All right, let's move forward. All right, mixtures. A mixture is a combination of substances. So you can think of a mixture as taking a jar, some kind of a little pile of pepper in here, right? And then you add to it salt, right? And if you add salt and pepper together and mix it up, what you're going to end up with is some pepper inside the salt, and that's a mixture, right? And you can see the little pepper flakes in the salt. So that's it. Those are the components. They're not really mixing together. They're mixing, but they're not reacting chemically, right? They're just sitting there next to each other. They're mixed up, like taking the example I always like are those when I used to take my nephews and nieces to the ball pits, where the kids would go jumping in the balls, and so that's really a mixture when they have all the red and yellow balls, and even the kids are in there all mixed in together. That's a mixture, okay? They're physically combined. There's no chemical reactions, no sharing of electrons or taking of electrons or giving of electrons. They're just mixing them up physically. All right, a solution is an example of a mixture. All right, so here we talked about salt and pepper, and that's when you distribute evenly. A solution is when you've evenly distributed all the solutes, all the components. The components of a mixture, that means the parts of a mixture, are the solute, right? And the solvent. The solvent is the thing that is doing the mixing, is usually more, there's more of the solvent than there is the solute. It's usually the solute is distributed within the solute is distributed within the solvent. So if you look here at the salt and pepper, evenly, let's say it's evenly distributed. Let's assume it's evenly distributed very well. Evenly, just a solid solution. So here you have this evenly distributed material, pepper and salt. Doesn't have to be perfect, but what have you. Because, which one is there more of, salt or pepper? Well, I hope you said salt. And so you can, I would say that the pepper is dissolved in the salt. So then, therefore, the pepper is the solute, and the salt is the solvent. So this is going to take some work for you to really make sure that these words that sound very similar are separated in your mind clearly. So the solute is distributed evenly within the solvent. So the solvent's the thing that does the dissolving. The solute is the thing that's being dissolved. All right? Doing the dissolving and being dissolved. Now, that being said, let me be very clear. This is another one of those points where people get confused all the time. Dissolving, when something's dissolved, in other words, it goes into solution, it becomes a solution. The solvent dissolves the solute. This is all physical. There's no chemical reaction in it. It may look like it's chemical because something seems to be going away or changing, but it doesn't really change. All right. And a suspension is a mixture of non-dissolved materials in water. So that means they're not dissolved. You can see them. You can see the different components clearly. So what do I mean by things seem to go away? That something is dissolved, right? And why do I say it's not a chemical reaction? Why do I say it's not actually gone away? So let's take a look at this just for a moment. Let me add sugar to water. Anybody that's made Kool-Aid knows that it tastes wonderful. Sugar water is great. Let's take this red Kool-Aid. So you have this red Kool-Aid material. And the red Kool-Aid material, you put sugar into it, so it's water. What happens? Let's say you didn't have any red. Let's forget about the red, and let's think about a system that has, instead of the red, let's think about a system that's just clear. Let's just water, just plain water, and you're adding sugar to it. Sugar is solid. It's white, right? You could even add cubes of sugar. So you have all these little cubes of sugar you're adding to there, and it's made of glucose and it's sweet. What happens when you add it to water? It does disappear. You don't see it anymore. Well, all you see is clear water. It looks like it's water. If you taste it, you can taste the sugar though, can't you? You can taste the sugar. Is there a way that you can think of that we could take this beaker of sugar water and take the water out and leave the sugar behind? If And there's an if-then statement here. This could be an experiment if you wanted it to be. If you have a beaker of sugar water, is there a way to take away the water and leave the sugar? Well, the answer is yes. There is. If you heat up the beaker to about 100 degrees Celsius, what you're going to get is an evaporation, or the water is going to start to leave. And that's called boiling or evaporation. So the water is going to evaporate. And eventually, if you want to boil it, you heat it up enough, 100 degrees, you get it to boil at room temperature, of course. I mean, at 1 atmosphere pressure. So the water evaporates, it goes away at 100 degrees Celsius, it boils at 1 atmosphere pressure. So water's going, it's called steam, right? This water turning to gas is called steam. That's a gas form of H2O. It's still H2O. It's H2O here, and it's H2O as a liquid. And if it were a giant ice cube, it would still be H2O. And that's why these are different phases. And when you change phase from solid to liquid to gas, it's all water. It's solid water, liquid water, gas water. So that's why we say that changing phases is also a physical change. It's not a chemical change. So if we get rid of all the water, what's going to be left after some time? What do you think is going to be left in that beaker? What you're going to get is that sugar back again. Now it won't be in cubes, but I'm just drawing it in cubes so you see it as sugar. You can think about it as sugar. So these cubes of sugar are now in the beaker rather than the water. The water's gone. So we put the sugar in. It won't be in cubes. It'll be more of a powder, and it'll be stuck to the side of the glass. But we put the sugar in, and it seems to disappear. It seems it's gone. Something's changed, you say. Well, the thing is that if you went ahead and did an experiment and heated it up and got rid of the water, what you would end up with is almost exactly, and only due to experimental error would there be a difference, almost exactly the same amount of sugar that you started with. So if you had 2 grams of sugar, if you put 2 grams in, what you get out is 2 grams of sugar. So what did that prove? What was all that about? Well, that proved, I think, or at least it should really give you a good indication that there's a lot of support for the acceptance of the idea that sugar, that changing phase, number one, and number two, that dissolving is a physical change, not a chemical change. How do I know that? Because when we dissolved it, it did not go away. It didn't change. The material really didn't change. It just disappeared. It got separated very finely in this very fine separation in the system. So when we added the sugar to the water, it got broken up such tiny little parts. It got separated from each other. The little sugar molecules got separated from each other, and they disappeared. So we call that dissolving. So, okay, pH is a measure of acidity. So we say, and it's a really weird thing to say, but the stronger the acid, the lower the pH. A lot of kids don't, I shouldn't say kids, a lot of people don't understand that. And it has a lot to do with math, and I could tell you it's a negative log of the ion concentration. And I could discuss it and show you mathematically how you derive it, but it's not really important for this class. What is important is you understand that it's a scale. It goes from 0, all right? It goes from 0 to 1, 2, 3, 4, 5, 6, and 7. 7 is neutral. At 7, it's not acid or base. It's not one or the other. This side is acid, That's 0 to about to 7 is acid. And then from 7 to 14 is base. So when we say an acid or a base, we're talking about the pH level. Now, what exactly is pH level? We'll have to talk about that later, but just so you know, there's these things called hydrogen ions. Now, we talked about hydrogen, and someone in one of the classes asked, well, if hydrogen has an atomic number of 1, it has a mass number of 1 rounded off, then does that mean that it doesn't have any neutrons? And the answer is yes, that's right. Hydrogen ions are basically a proton, a single proton with a hydrogen atom. That means a neutral atom is one single proton and one electron. That's the simplest atom there is. There it is. There's hydrogen. Now, if we went ahead and took the electron away, that would make this hydrogen ion. And of course, it would be +1 charge because we got rid of an electron. So if we do that, we end up with H+, and H+, or hydrogen with, that's a proton with no electron, is simply a proton, right? H+ ion is just a proton. So pH is a measurement. If you have a beaker, again, another system, and you have some kind of liquid form, some solute, you could have some solvent, or the solvent might be water. The solute will be hydrogen ions. These hydrogen ions are single protons, are floating around here. The more of these hydrogen ions you have floating around in here, the lower the pH. It's a reverse relationship. So so this is the hydrogen ion concentration, and the square brackets mean concentration. So the larger the number, the pH value, the less of these hydrogens you have. The lower the pH number, more hydrogen ions. The higher the pH number, less hydrogen ions. Both acids and bases are both reactive. They can both be caustic. So, lye, for instance, as a pH of about 14. Sodium hydroxide as bleach. Sodium hydroxide, very, very, very basic stuff. And what you'll see is it's around 10 or 12 or 14, depending on the concentration. Where an acid is the opposite. And it turns out that an acid can have, go anywhere from 7 to 1 to even any one of these which means all this means is that there's more hydrogen ions in the solution. I know it's crazy that the lower the number, the more hydrogen ions, but that has to do with some math that I could show you, but we really just don't have time to discuss. That goes back to that pH, or the negative log of something. So pH is below 7 is acidic, above 7 is basic. So that's something that you really just need to make sure you got in your head. Below 7 is acidic, and above 7 is basic. So if I tell you a solution has an acidity of pH of 3, then you know it's an acid. If I tell you something has a pH of 9, then you know it's a base. All right, let's move on. Well, here's some examples of that, right? So 0, pH 0, battery acids around there, stomach acids around 2, apple juice is about 3. We have these indicators that change color called pH hydrian paper. We have litmus paper, several different kinds of indicators that change color depending on the pH. And neutral is, of course, 7. And so when you look at pure water, it's exactly 7, right? Coffee is a little acidic, it's 5. Apple juice is 3. Household ammonia is at 12, and drain cleaner, Drano, is 14. So drain cleaner is pretty much lye, and battery acid's pretty much, it's not quite 0, but it's pretty much the strongest acid. So you go from battery acid to drain cleaner, and everything in between. Almost every substance that is an acid or base, we can separate it. All of the substances that are acid and bases fall within this range. So the acid is anything less than 7, a pH of 7, and 7 is neutral. And then anything more, pH is larger, greater than 7, it's base. So when we look at water, water is so important because outside, remember that whole schnapps. Well, water is part of schnapps, isn't it? If we take a look at water, H2O has 2 hydrogens connected to an oxygen. Water, and this is schnapps, CHNOPS. And in case you forgot, it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Water, it has oxygen and it has hydrogen. So it has 2 of the elements of schnapps. And that makes sense because water ends up making anywhere from 70 to 95% of organisms on the planet Earth. So you're made up of about 70+% of you is water. You are a solution. Your cells have solutions in them. They have varying concentrations of solute or varying amounts of solute in the solution. So when we talk about schnapps, when we talk about this water molecule making up most of organisms found on the planet, it's not surprising that the atoms that or elements that make up water are in schnapps, right? Because water is a 70 to 95% of most living things, and these are the elements, the main elements in life. So that wouldn't be surprising at all. Now this is going to be very important for you to understand. And it's going to be important for you to understand because when we start talking about these atoms and these molecules, when we start talking about these things called biomolecules or very large molecules, you're going to have to consider that these molecules are not bonded together evenly always. Sometimes a strong atom is bonded with a weaker atom. So let's take a look at water, for instance, and we're going to use water a lot this year as far as the discussion point because it's so important to life. But water actually has a partial negative charge. This is the Greek delta, lowercase delta, called, it looks like a little S, but it has a little loop on it. That's a Greek letter delta, right? And it means partial. That equals a partial charge. We looked at just give me a second. We looked at ions, and ions, one got taken, the other given, and one became positive, the other negative. Well, there are these things that happen with partial charges. So this ends up being partially negative. This is partially positive. This side's partially positive. So between these bonds here, this is partially negative, this is partially positive. How is it possible to have a partial charge? Well, these three atoms, oxygen, these 3 atoms, but 2 elements, right? Oxygen. Now, this is something I'll go ahead and state it. I try to hint at it throughout the video, but let me state it clearly. I will ask you a question. I'll show you a molecule and ask you how many elements are in this molecule, and then I'll ask you another question, how many atoms are in this molecule. Hopefully you can tell me with water, for instance, there are 3 atoms and 2 elements. If you don't understand that, it's something to really discuss with your group during the activity or during your study group session, and know how to figure out how many elements versus how many atoms. Okay, so here we have 3 atoms, 2 elements. It's water, and I said that they're partial charges, that they're bonded covalently, so they are sharing, but they're partially charged, which means there's more electrons around the oxygen most of the time versus around the hydrogens, and because of that, the hydrogens become partially charged, a positive charge. means is that when you're looking at these atoms sharing, oxygen is so much stronger that it keeps the electrons around it more often. So you have to think about this sharing, where sharing covalently is generally even. If it's evenly shared, we call it nonpolar. It's just like two people that share a car, and each one of them gets it for you know uh, 12 hours a day. Then they're evenly sharing the car. But if two people are sharing the car and one is older or bigger and takes the car, you know, 18 hours out of the day and only gives the car to the other person while he's sleeping for a couple hours, that's unevenly shared. Well, sometimes what you get, for instance, and in the example of water, is you get this oxygen atom that is able to take the electrons from hydrogen and keep them most of the time. So, for whatever reason, water is the water molecule is able to take the electrons, keep them most of the time, and so oxygen becomes negatively charged and hydrogen becomes partially positively charged. So oxygen is partial negative and hydrogen is partially positive. So that being said, when you're dealing with an atom like this, any atom that has this kind of structure, you're going to get these really really weak forces that attract it. Where you had sodium was a +1 and chlorine was a -1, they have a fairly a stronger attraction to each other than something like oxygen. Now, this is a covalent bond, so naturally it's a stronger bond. But what ends up happening is if you look at now an attraction between two water molecules, and you see that this has a partial negative charge and this has a partial positive charge. So this has a partial positive charge, this has a partial positive charge. This has a partial negative charge, this has a partial positive charge. What happens is that this that these atoms, these molecules in the start to arrange each other. So this negative starts to attract the positive, and this negative starts to attract the other positive, and the molecules turn. They turn in such a way as to line up, and what you get is this lining up of water. And it lines up over and over again. And why is it lining up this way? Because there's this attraction between the partial negative charge of oxygen and the partial positive charge of hydrogen. And so it's partial, it's not an ionic bond. They're still covalently bonded. But because there's a negative side and a positive side, there is a negative and a positive side, we call these polar. So polar literally means that the charges are not even. There's two sides, so like a north pole or south pole, like the positive and negative pole of a magnet. So whenever something's polarized, there's two sides. So here we have this these poles. This is each hydrogen is partially positively charged. Each negative is partially. Each oxygen is partially negatively charged. And so what you end up getting is this alignment where the opposites attract and the like charges repel. And that's called, this bond here is called the hydrogen bonding. So it's not really a bond. These are not sharing electrons. And it's not an ionic bond, but it's a very weak intermolecular bond that attracts one molecule to the other. Notice that these are molecules. This is a molecule of water, this is a molecule of water, and this is a molecule of water. But it's the partial charges that attract each other that line everything up. And so this is a pulling between molecules, where this is the pulling between atoms. This is much, much stronger. This is much, much weaker. So it's because water is polar that water has these really, really interesting properties. And so one of the things that people don't think about is water is really sticky. It sticks to itself, it sticks to you. Think about it. When you're showering, and you might think, well, I feel clean after a shower, only because you use something to take the water off of you. And that's called a towel, right? So water molecules are sticky, and it's really mind-blowing when you think about it. When you get in the shower and the water's running on your skin, it feels clean. But when you're done, when you turn the water off, what is your body? It has no clothes, so there's nothing wicking it up. But what's on your body still? Water. Well, how's the water staying on your skin? It's staying on your skin because water's sticky. And it's sticky because it's polar, right? Now, I'm not talking sugar sticky, but it is sticky. And because water is polar, it has adhesive properties. So it sticks to you like glue. Very, very weak glue, but it does. It has cohesive properties, which means they stick to each other. So if you think about it, if you ever did this experiment, I think it's safe to do it at home, but you should check with your parents. If you have this penny, you're looking at a penny by the side, it has little ridges, and you took water and you started putting one drop of water. Let me redraw that. One drop of water onto the penny at a time. What you're going to get is this mound of water, and you can look at it from the side. And this is water. You can see it's clear. It sits on, but here's a question for you: how is it that this is made of molecules, right? This water droplet's made of molecules, and the water droplets made of molecules so's the water on the penny. So now the question is, why does the water molecule stick to it? Why is it that hold on a second. So the water droplets are going onto this penny, and the question is, why is it that the water just doesn't run off? Why does it stick up, stick, and why is it stick? What is it sticking to, and what is it doing when it's making this mound? Well, it doesn't run off. It's because the water molecules they're all sticking to one another. And because water is sticky, it sticks not just to other things, but it sticks to itself. What you see water just sticking to itself, and all these billions of water molecules all one next to the other sticking to one another. And that's that particular property, that stickiness of water, that when it sticks to itself, is called cohesion, right? It's this cohesive effect. Where water, when it's sticking to other things, we call it adhesive. So adhesive is when it sticks to other things, and cohesive is when it sticks to itself. Co, right? Together. To, right? All right, so water is able to absorb large amounts of heat. As a result, lakes, oceans stabilize the air and land temperatures. So just know that water is able to suck up a lot of heat, right? That's the second point you have to remember. And water absorbs heat when it evaporates, allowing organisms to sweat, to relieve themselves of heat. So if you have your skin of your arm, and you start to pull these little beads of sweat on your arm, and we could talk about phase change energy, but we won't because we don't have time. But what happens is the water evaporates, and when the water on your skin evaporates, and that's what we call sweat, right? Sweat it's mainly water, although there's urea in there, and there's salt and all kinds of other things. Anybody that's actually done a lot of exercising for a period of time, you've probably felt the salt crystals on your skin. That's because the water evaporates and the salt stays behind. Well, in order for water to go from the liquid phase, this is the liquid, right? And remember, we said it was a physical change, right? To the gas form, we call this water vapor, right? And this is liquid water. and it's a solution, but liquid water solution because there's things dissolved in it, urea and salt, etc. So liquid water, I don't know why I put liquid there twice, but so we have liquid water is on your skin, and as it evaporates, it requires heat. So the heat from your body goes into this water, and when it does that, the water evaporates and takes with it into the air your heat. So all the heat moves with the water vapor, with the water, when it goes from liquid to gas. That's what we call. That's why we. That's how your skin cools you off when you're sweating. That's why you sweat, to cool. Because water expands and it freezes, ice floats, and that prevents lakes and oceans from freezing solid. Now let's think about what that means. So if you have, if you have this bowl, and let's think of the bowl as a lake, and here's a hill, there's grass, and there's maybe a tree. All right. And on this side is some more grass and some more trees. There's a little fish in here. A lot of fish and turtles and frogs and whatever. When winter comes, what happens is that the surface of, you ever wonder how, by the way, have you ever wondered how is it that fish survive the winter in ponds especially, but lakes? Well, what happens is the water on top freezes, and because ice is less dense than water, our solid water is less dense than liquid water, the solid water freezes and stays on top. So the staying on top, the floating, happens because water is less dense when it's solid. That's not the case for most materials. Most materials, the things that are solid, are more dense. The liquid form is less dense. Well, not water. Water's reversed. And because of that, this ice sheet, right, sits on the surface, and below that ice sheet, it's still liquid water. So the fish, the turtles, etc., can survive. The turtles and amphibians, the reptiles and amphibians usually bury themselves under bury themselves into this mud and muck underneath inside the water, deeper into the pond soil itself at the bottom of the pond. But what have you, the point is that this ice sheath, this ice shelf, what it does is it protects the liquid water underneath from freezing. If this was not true, if ice did not float, if ice was like most other things, if the solid form of water was more dense than the liquid form of water, then what would have happened is that ice wouldn't float, it would sink to the bottom, and things would freeze from the bottom up, and that would just kill everything. So there would be impossible for life to exist on Earth. So water's very property of, or ice floating, is actually one of the reasons life exists on this planet. Then it says water is able to dissolve many substances so that water inside and outside the cell is able to carry nutrients in and around the cells and waste away from the cells. So we call this property of water, we call water a universal solvent. So it's not really universal, but let's just say it has the ability to dissolve so many different things, whether they were polar or non-polar. This universal solvent called water is really a good solvent. It really dissolves just about anything. Now, you know that because when it's time to clean, most of us go for a bucket of water. When you go wash your hands, you wash it in water. You don't wash it in oil or you don't wash it in Coca-Cola. You wash it in water. Why? Because water is a universal solvent. We know that intuitively. So it'll dissolve all the muck on our hands, especially if we had a little soap when we have grease on it. It's still a very much a universal solvent. All right, well, that's it. I think that's way more than enough. It's only 17 slides, but I'll finish the rest of it on Thursday and give you some more practice problems. And then remember, Wednesday is I'm sorry, I'll give you more. We'll finish the rest of this on Wednesday, and then the following Wednesday is your test. So that should give you enough to study for a couple days. All right. See you on Wednesday. We can take these, and can I draw it like this?
Yeah, that's how sure.
And I can draw I won't put any H's or O's or anything. And we're just going to assume that you know that each little dot, each corner is a carbon, and you know that it really looks more like this, right, or this one. But we're not going to worry about all that, right? We're just going to draw them like this. And with this, actually, this chain can go on, and it could split. It can move on different areas. It can branch. You can have all kinds of shapes. Does that make sense? In long chains of carbon. So this thing's called a polymer. Not a polymer, but a poly. Poly means many, many mers. What mers? Monomers. A monomer is one, right? So many of these glucoses, let's say there's glucoses, many glucoses. So it turns out that there's many different kinds of polymers of carbohydrates. And glucose is kind of a really important molecule, a very, very important molecule. You'll see it throughout the whole year. It's probably the most important molecule in biology. Maybe oxygen is a little important, but certainly carbon. And it's because this is what you remember, that glucose was part of a chain. The polymer was one of those three that we talked about, that you just heard. Glycogen, or it was starch, or it was cellulose. That's all. Those were the three polymers of carbohydrates that we talked about. All of them have what molecule, what monomer? Glucose. The second one asks you what? Somebody read it. Yeah. But when it comes to polymers and monomers, glucose is the big one. So let's look at carbohydrates. Let's think about it. These side conversations are going to be an issue. So let's take a look at what we looked at before. C6H12O6.
That's the formula of glucose.
That's right. That's the kind of stuff that fructose is made out of, and glucose and galactose. All three of them are C6H12O6.
Yes, but one is mercury.
Not all carbohydrates are C6H12O6, but you know what is all carbohydrates?
What?
All carbohydrates store and release energy. That's for sure. And you know that if you took these wood chairs that are made of cellulose, right, and you threw it on a fire, would it release energy?
Yes.
Yes, it would. If you ate sugar, does it give you energy? Yes. Sure does. So it stores, these things store energy. Now, what are they made of? They're made of carbon, hydrogen, and oxygen. Right? Carbon, hydrogen, oxygen. That's what they're made of. So carbohydrates don't have any nitrogen or sulfur. If you have a molecule that has nitrogen, sulfur, and etc., that's not a carbohydrate. Does that make sense? Mm-hmm. That's something else. So CHO, and then the other thing is, look at the ratio. What is the ratio between these two, and then what's the ratio between these two? Who can tell me?
6.
This is 6 to what? 12. And what's this one?
12 to 6.
Or 12 to 6. Can I just rewrite it as 6 to 12?
Yeah.
So they're both 6 to 12. Can I make that smaller?
Yeah.
1 to 2. That's right. Somebody knows their math. So this is 1 to 2. So the ratio is 1 to 2. So when we look over here and we see in all carbohydrates, what you have is 2 hydrogens for every 1 oxygen. 2 hydrogens. Oop, I reversed it, so maybe I shouldn't have reversed that.
2 hydrogen to 1 oxygen.
So we have 2 hydrogens. 2 hydrogens for every 1 oxygen. So hydrogen and oxygen, and this is hydrogen and this is carbon. So for every hydrogen has 2 for every 1 oxygen and 2 hydrogens for every 1 carbon. That's true of all carbohydrates. All carbohydrates. Do you understand? Does everybody understand when you look at a chemical compound, this tells you what? What does this 6 tell you?
How many? 6 carbons.
How many? That's right. How many carbons? And this 12 tells you?
12 hydrogen.
And 6. See, we good?
Yeah.
All right. So that's it. That's it. That's all you need to know. You know that. We can move forward. All right. So these things called monosaccharides. I'm telling you right now, they're important, but we're not going to worry about it right now. If you know it, great. But I'm going to tell you right now, this disaccharide stuff, you can just, it's not going to be on the test. They're important, but you don't have to worry about disaccharide. Monosaccharides, for sure. What's a monosaccharide? That's your monomer. What's an example of monosaccharides? Glucose and fructose. Right? So what we want is an example of monosaccharide. If you want an example of monosaccharides, you're going to look at glucose and fructose and galactose and ribose, right? All these sugars, they're only made of 1, right? Mono means 1. So 1 sugar, one molecule of this stuff, 1 monomer.
So like
If you had 2 of them put together, like fructose and glucose makes sucrose, there's a bunch of disaccharides, so it's 2 put together. But what are we really worried about? What am I trying to ask you to focus on? 1, and then what's the other? Poly. 1 and many. I'm asking you, don't worry too much about the dyes. That's important for health and for food and all that. But what you really need to worry about is the many and the mono.
Mr. You said monosaccharides are mono.
Say that again? Monosaccharides are monomers. Yes. I made that too small. Okay, can I go on?
Yes.
Almost.
Oh my goodness. And
Wait, like 20 more seconds. Count down.
What are you writing?
and go remember it. Watch the video, guys. Watch the videos. Leave space and watch the videos. We got to move on. I'm trying to keep to target, and it's warm in here today. The air conditioner must be off. All right, so when we're looking at polysaccharides, there's 4 polysaccharides you have to know for the test next week. 4. And they're up here, and yes, I'll zoom in for you. And I'll tell you, these are the 4 big ones. Plants make starch. The starch that they make is to put it away for food. Plants make starch to put it away for food. Did you ever ask yourself, what do plants do in the wintertime when they don't have leaves?
They do this.
They make starch.
They make starch during the spring, summer, and fall. When they lose their leaves, they can't make any more sugar. They make their own food, right?
Yeah.
Plants make their own food. Who do they make food for? For them. They don't make it for us. We steal it. Animals are thieves. That's all we do. We steal it from plants. No animal can make their own food. You can make it a nice word if you want, but the bottom line is we steal all our food from plants. Plants work hard all spring, summer, and fall. Come winter, at least in the north, they lie dormant. But they're still eating, they're still alive, they still got to live. What do they eat? Their starch, their stored sugar, their starch, that's right. So those potatoes that we dig out of the ground, we're killing that plant because we want their potato. They don't need us to plant them. So we take the potatoes, we take the yams, we make our food, that's great. But understand that they did not make it for us. They made it for themselves so they could survive the winter. Now when it's our turn and we need to put stuff away, like did you ever think, do you eat at 12? Like you go to sleep at, I'm gonna tell you the time you should go to sleep at. You go to sleep at 9 p.m. You're asleep. Some of you do go to sleep at 9 a.m. But we go to sleep at 9 p.m., right? And you wake up at 5 or 6 a.m., right? Some of you wake up at 4, whatever. So what do you do during the interim when you're sleeping? How do you get energy to sleep? You're alive, aren't you? Are you alive when you're sleeping? Yeah. You're breathing, you're moving. Some of you move too much. Some of you snoring. Some of you snoring. That takes a lot of energy. Where are you getting that energy? Where are you getting that food, that sugar? You're not eating.
Your food that you had earlier?
Not your fat, although it could be from your fat. From your glycogen. See that glycogen? It's up there. Glycogen. You store sugar in your liver. When you eat breakfast in the morning, which is why you need to eat breakfast. I don't care what it is. As long as it doesn't kill you, it makes you stronger. You need that sugar, that fat, that protein in the morning so that you can make it through the day. Come 2 o'clock in the afternoon and you're exhausted, it's because you haven't eaten enough or you haven't drank enough water or you haven't slept enough. That's it. It's not because it's boring. If something's boring, you make it interesting. You can see that. You see little kids. Have you ever seen little kids that are bored? They'll take their little cardboard box and they'll make a fort. When my father used to take me to the racetrack, you know what the kids and I at the racetrack would do, all the kids at the racetrack? We take all the little racing tickets that people threw on the ground and we make little boats out of them. Or we take cups of water, you know, the thistledown's on a hill, and we pour a little water down the hill, and we bet to see how many tickets, because we didn't have money. So we just bet the tickets to see how fast, which stream of water will hit the bottom of the hill first. If you're bored, you find something to do. When you're falling asleep, it's because you're not sleeping enough, you're not eating enough, or you're not drinking enough. That's it. People that are bored talk to each other. People that are bored draw, doodle. They daydream, but they don't sleep, right? So, glycogen is the stuff that we put away when we eat. You know, we eat 100 calories. Let's say we eat 400 calorie breakfast. We use up 100 calories to catch up. We put the other 300 in our liver, and in the form of what? Glycogen. You're right, storage, glycogen. Not like starch. Who uses starch? Plants. We eat the starch. We love the starch. I love my potatoes. But we can't make starch. We can make glycogen. We can put away glycogen, and then when we're going through the day before lunch, and we're like, oh my gosh, another lecture, another lab, another essay, another math problem. How do we get the energy to do that? Our liver spits out that sugar into our blood so our brain can keep going. That's glycogen. What about cellulose? Where in the room is cellulose? Did you ever play that game, Where in the World is Waldo?
Yeah. Oh, yeah.
Well, where in the room is cellulose?
Our body?
No, it's not in your body.
In the plant cells.
Could you read? It's in plants. Are there any plants in this room?
The chair.
The chairs. Where else is cellulose?
The paper.
The paper.
The desk.
The pencils.
The desk. The pencils, if you have wooden pencils. So this is what we use wood for. But wood is used by plants to make their bodies. Their bodies are cell walls. You've heard of cell walls, right?
Yeah.
They're right outside their cell membranes. Only in plants and in bacteria and in some and in fungi do you have cell walls. They need cell walls because if they didn't have cell walls, they would burst open. They would fill up with water and burst open if it flooded. What are the Texans doing? What are Texans doing because of the flood?
Floating.
Okay, they're vacuuming. They're getting up and leaving. They're leaving. Yes, they could float away, or maybe they could helicopter away. Hopefully, they drove away before the floods came. But they leave, right? Can a tree get up and leave?
No.
So they got to stay there, and they got to deal with all that water. The cell wall stops them from bursting their cells. So that's why that's so hard. That's why you're able to sit on it. Because that tree has to be able to hold itself up and be able to resist all that water. Does that make sense? Yeah. The same for bacteria and fungi. So if the thing can't get up and walk around, it probably has a cell wall. Yeah. In a way, yes, except we use bones, right? Right. But we don't. But it's different because this is made of sugar and plants don't move. Does that make sense? Don't move around a lot. They do move. Let's be clear on that. Plants do move. A Venus flytrap moves, as many a fly has noted. All right, so chitin. Who has ever seen a beetle skeleton, a beetle exoskeleton on a tree or on a branch? And no one's ever seen that?
No.
I have.
All right, take out your phones and look it up. Beetle. Look up cicada exoskeleton. Cicada exoskeletons. Cicada. Spell it and Google will fix your spelling for you.
What did you say again?
Cicada exoskeleton. Oh, you're trying to do the audio one? Go ahead, cheater.
What is this?
Do you see it?
No.
So
It's a bug.
that's that's it. Cicada exoskeletons. What it is think about it. These insects, these things that we call arthropods, we call them arthropods because they have this. Their hard part is on the outside. Our hard part is where? On the inside, right? On the outside we have our soft parts. These insects have hard parts on the outside. We call them exoskeletons. The whole group, it's not just insects. It's spiders and beetles and centipedes, right? Scorpions, they all have, on the outside, they have a skeleton. Their hard parts on the outside. That outside, that hard outside that you just looked at, is made of chitin. And what is chitin made of? It's a polymer of what? What's the monomer for chitin? What's the monomer for all of these?
Sugar.
It's sugar, monosaccharides. So all of these are polysaccharides. All these things are made of sugar. So that makes you think twice when you say girls are sugar and spice and everything nice. Because they could be a scorpion. All right, so are you ready to go on? All right. Remember, you're right. What is it? Lipids. Lipids are a type of biomolecule. It's another. This is not a polymer. Lipids are not polymers. They don't have monomers.
Isn't it non-polar?
Yeah, we're going to talk about nonpolar and polar. Very good. That's kind of the key point here.
They non-polar.
Yeah, I'm sorry. They're nonpolar. I'm going to write it all down now, so I don't really mind that you can't see it. Is that all right?
Yep.
All right. So I'll check them off as I go over them, so make sure we don't miss anything. So first thing I want to talk about, somebody just mentioned, is let's talk about polar and nonpolar. So I'm going to give you one of the questions on the test right now.
Okay.
So water's going to be your big polar molecule. That's the one. This is the one you got to know because I'm going to come at you with water. This is a polar molecule. It's partially negative on the oxygen side and partially positive on the hydrogen side. That's what that little delta means. It means partially positive, okay? So this thing is polar.
This thing is polar. Polar molecules have a partial positive. They have two sides, right? They have two sides. That's what polar means. They have a positive side and a negative side. They have a positive side and a negative side. Negative, positive. So they can line up, right? So they can pull on each other. That's why water's sticky. All that stuff we talked about. Okay. So now let's take a look at polar. Now let's take a look at something else called nonpolar. Now there's nonpolar things are things like lipids. And I'm going to use this X because there's going to be an exception. I don't want to talk about it right now because it'll just confuse you. So I'm going to say X. And X has then you have a bunch of carbons, a long chain of carbons.
He wants to write that.
Yes, I would draw this as an example. You're definitely going to need to know this. I'll give you another test question. You're going to see this molecule on the test. Water is the example for polar, right? Everybody has that. And if you have a long chain of carbon and hydrogen together, then we call that what? Nonpolar. Now let me be clear. Nonpolar means that there's nothing, all the atoms have pretty much the same strength. They share evenly. I'm going to go through an example with you in just a second. Say what now? Yes. So let's go through the example. First, I want you to see that what I'm telling you about this is that this long chain of carbons, there's no, let me rephrase this. They share evenly. They share evenly. All the electrons are shared evenly because they all have equal strength. So I'm going to give you two scenarios. Are you ready? It's just as an example, let you think about what this means. Your mom goes to Switzerland, and she met this really sharp guy who has all this money. Let's assume she's not married. Okay. Let's assume she's not married. Please let's not start any trouble. So they go off to Switzerland, and the guy buys her this amazing chocolate. Okay. And she's like, "Oh, I gotta share with my children." And she goes, he buys all the kids chocolate. He's rich. Really expensive chocolate. Willy Wonka factory, Angels of Tears helped mix the chocolate. Only the Oompa Loompas mixed it. No human hands have touched it. So here it comes, this big old chocolate bar. Mom gives you this big old chocolate bar. Say, "Here, honey, share it with your little brother."
But
so you got to share, because if you eat this thing, you know it's a wrap. Somebody's getting it. So that's right. So what will most people do? Not everybody. Some people are going to be nice. I'll be honest, I probably wouldn't be that nice. I would probably take a little piece of chocolate, hand it to the little kid, and I'd be sitting there with this giant chocolate bar eating in heaven, right? That's what most people would do. That's sharing unevenly. That's uneven, right? So that would be this one. This is uneven. They're sharing the electrons unevenly. So around the oxygen, you have its negative because the oxygen is that big brother that takes the electrons more than the little brother, hydrogen. The little brother, oh well, I got to stick around. I'm sharing. You're sharing, right? You can tell Mom I shared the chocolate bar. I did. It just wasn't even.
I'll be doing that to my brothers.
Yeah, I used to do it all the time. I was the biggest one in the house. Nobody messed with me.
I thought you said.
And if they ever told, no, I'm kidding.
You never hit your brother.
I'm kidding.
You never
I
hit
really
your
am.
brother.
I have never hit my brother.
I'm the youngest one, and I hit my brother. It was all boys.
All right, so yeah, mostly boys. There's one girl. We used to fight all the time. But then there was a difference. Now let's say now Mom brings home that chocolate. We're gonna fast forward. Different scenario now. Okay. Now it's you and your sister, but you and your sister are twins, both the same size, and she hands you both the chocolate at the same time, so she knows you have it. And she knows how big the chocolate was. Now, is that whole uneven thing going to go over very well?
No.
No, so you're probably going to share it evenly, right?
No.
Yes, you are, because it'd be a fight, and Mom will take it away. You'll never get another chocolate bar again.
I mean,
So,
they
the
don't
best...
take it away.
No, you give her the smaller.
No, they won't, but she won't ever get you another one. Her and that rich guy leave you alone
But
with
you
your
said he was rich and he bought each kid.
All right, okay, shh.
One.
You gotta give her the smaller half.
Wow, we're just gonna get bogged down in the details of the story, are we? So my point is, when the two things, whether they be people or atoms, when they're equally strong, in equal power position, right? They share evenly. And so when they share evenly, there's no partial charge. Does that make sense?
Yes.
That's all I'm saying. So that's why this thing's nonpolar. It's nonpolar because there's no charge on it. It's nonpolar because they share evenly. So this shares evenly, so it's nonpolar. Are we good with this?
Yes.
So polar means that they share unevenly and they have a positive and negative side. They have a positive and negative side because they share unevenly. Nonpolar means they share evenly, which means they don't have a positive or negative side. It's just it's all neutral. So you ready for the rule? Now that we went through all that?
Yes.
Here's the rule. Like dissolves like. Like dissolves like.
You're right.
Did I spell dissolves wrong?
Yep.
Oh my God. There's your S. Are you happy now? Like dissolves like. I just wrote it big, man. Are you happy now? Like dissolves like. So what does that mean? Can somebody tell me what that means? Yeah, go ahead.
What the things, all right, I don't want to use like, but the things that are alike, pretty much.
What are the alikes that we're talking about? What are we talking about with likes? Neutral, that's right. Or what's the word we're looking for really? No, nonpolar. The nonpolar stuff, that's right, you did. The nonpolar stuff dissolves what? The nonpolar stuff. Nonpolar dissolves nonpolar. And then what? Then polar or charged dissolves what? Polar or charged. Like dissolves like. So you ready for your examples? I can promise you might see some of the same examples on the test. Clue. I will be paying attention to the examples. Yes, sir. I don't want to say names. So yes, sir. Yep. Remember when I'm recording, I don't like to use people's names. Okay, so like dissolves like. So let me ask you something. How come? Do you ever notice girls paint their fingernails? Guys, you ever notice that? Your mom or some of your girlfriends or whatever paint their fingernails, and they get real fancy ones, don't they? Are y'all listening? You gotta listen to the example. I don't mean this to be girls. I don't mean this to be a whole big thing. Just listen to the example. So you're painting your fingernails. They dry their fingernails. And if you ever watch a girl paint her fingernails, she'll paint them. Now she'll go. Wait till it dries. Honey, okay. So they dry. I've seen my sister put her fingernails right in front of a fan and get them to dry. So they do that. So now they're dry. Do you ever wonder why when they go wash the dishes they don't just dissolve? Why don't they dissolve?
Because it's not like. They're not like.
They're not alike. What's water?
Polar.
Polar. So what is nail polish?
Non-polar.
Ah, see that? That's going to be something like that is going to be a question on the test.
Can you say it again?
So listen to her logic. See, I've been having a lot of kids think really beautifully today. A lot of fantastic thinking. So if your fingernails are painted and they're dry and you stick them underneath water and you wash dishes, they don't dissolve.
Some polish do.
Yeah.
Well, most don't.
That cheap stuff.
All right. I need focus, okay? So if you have, let's just go ahead and clarify. If we have good nail polish and it's dried, and you go wash the dishes, they don't fall. It doesn't dissolve. It might chip off, but it doesn't dissolve, right? Okay, shh. So it doesn't dissolve. What does that tell you? If you know water is what? What is water? Polar. So what is the nail polish? Non-polar. Because it's not dissolving. Now let me give you another example. You ready?
Yes.
Wait, I have a question.
All right, but I'd rather you guys use the office, but go ahead. Excuse me, yeah.
Okay, so would that make nail polish remover polar? I mean non-polar?
Non-polar, that's what we're saying, yeah.
Okay.
That's exactly what we just said, right? All right, so now let's go ahead. It's a good question. It's really good thinking, all right? We're good? All right. So now let's think about this. You ready for the next one? So I come in one day and I see this on a table. All right. Now I try to use some water and a rag. It won't come off. Somebody used this lying marker called permanent marker. It's a lie. It's not permanent. So they mark it so it doesn't come off with water. What am I going to use? Alcohol. I can use alcohol or nail polish remover, and then if I use either one of those, what happens to this? It goes away. And that's what it dissolves under the rag, and that's what we call. So what does that make alcohol or nail polish remover? Non-polar. See that? It's a non-polar solvent. You see how easy that is? Yeah. Okay. I mean, one more example that happened in my life that taught me a lesson the hard way. Very costly. It cost me a lot of money, a lot of embarrassment. More embarrassment than money, actually. So but a new pair of glasses, just like these, actually, very similar to these, and they transition, and they're all fancy, which is important to those of us who wear glasses, right? And I got some smudges on them, and so I tried to wash them off with some soap and water, but they wouldn't wash off, right? So I'm sitting there with a lens cloth, some soapy water, and it doesn't come off. So I thought, well, I'm a biology guru, right? I'm a genius. So I said, I went to the cabin, got my wife's nail polish remover, and I put on a rag, and I started wiping. And the smudge started to smear away. It wasn't coming off before, but now it's coming off nice. It keeps coming, but it gets smearing and smearing and smearing and smearing. It turned even more and more smearing, where I didn't even know where it was coming from. Then I rinsed it all off, and I looked, and I had dissolved my glasses. I dissolved my glasses. And it turns out my glasses are not made of glass.
Wait, what?
I'm like, what? They're glasses. No, my glasses were made of polycarbonate. They're plastic.
So
Which is what? Non-polar. Non-polar. So the non-polar solvent dissolved my non-polar glasses, and I was left with a $200 bill for new lenses in my glasses. My wife was not happy with me. So.
Did she laugh at you?
Oh, I didn't. Yes, she laughed at me. But the story I told the people because the eyeglass people was like, "How'd you do this?" I said, "Well, see, what happened was." So I just let it go. But like I remember it when I asked you. Not a good idea. So one last thing about lipids, and I think we're going to be done for today. What time is it? 1:10. So we got time. Good. We might actually finish more than the rest of the class. Yeah, saturated. I'm gonna explain to you what how saturated fat is, because you've heard of this, right?
Yeah.
And you probably you always want to know what it was. And there's probably some things you didn't notice before. Let me ask you this: corn oil at room temperature, is it solid or liquid or gas? It's liquid. Butter at room temperature, solid, liquid, or gas? Solid. There's a reason for that. That's because this is saturated and this is unsaturated. We'll talk about what that is in a minute. But before we do, it's important that we talk about solid, liquid, and gas a little bit. So when we have a solid, when we have a solid, oh, I shouldn't draw it that way because that's too obvious. So we have a beaker. If we have a solid in here, it's going to take up little corners of the beaker, right? And this solid, you know, has so many molecules in it, and everybody's happy. It takes up a definite shape, right? And there's a definite space. And for you to change the shape, you have to break it, right? You can't easily. So this is solid. Now, without adding anything to it, except heat, I can add temperature. I can increase the temperature. Increases this way. And that same beaker, after some time, after I give it some time, that same beaker, all of a sudden, I got this at the bottom.
Right.
Now there's no definite shape.
No, it's a liquid.
Now it's a liquid. The same amount of matter, right? I didn't add anything to it, did I?
No.
But it takes up the whole container up to a point, right?
Mm-hmm.
Up to a point. Let's say this container's closed, by the way. Let's say it's closed all the way. It's important for the next one. So this is a liquid. What do we call it when we go from a solid to liquid? Melting. We call it melting.
Oh, I thought you wanted a more.
Yeah,
I was
no.
gonna be stupid.
No, melting. And if we go the other way, what do we call it?
Freezing.
Freezing. Isn't that interesting? So butter's frozen at room temperature. Butter's frozen at room temperature. Isn't that weird?
But don't it start to melt?
Ice, it
Yeah,
kind of,
it
but
gets
if it gets hot. But if it's 70 degrees Fahrenheit, it's solid. It might be soft, but it's solid. All right, so if we heat it up a little more, what happens to that? No, we're not adding anything, right? No dissolving. Dissolving is it becomes a gas. Evaporates, and it fills up the whole chamber. We know this because we can fill up a balloon with this. There's no more dots in any of these. All of these have the same number of dots. Assume that. And what do we call it? We call it evaporation. I'm just going to put evap. And if it happens real quickly, we call it boiling, right? Mm-hmm. So it's boiling or evaporation point, and that's obviously a gas. So that's solid, liquid, and gas. Are we clear?
Yes.
Almost all substances can go from solid to liquid to gas. All depends on temperature and pressure. All substances you can melt butter and turn it into a liquid. You know that. But with butter, with these kind of molecules, if there's any oxygen around, with these kind of molecules, what happens before they melt, before they turn into a gas, what'll happen is that they'll burn. They'll burn. So it's not easy to have these big ones turn into gas. These big carbon chains. But almost anything, you can have solid iron, you can have liquid iron, you can have gaseous iron. All right, so just about any, definitely all the elements, but almost all the compounds can be solid, liquid, or gas under the right conditions. So you can have liquid oxygen. That's what divers put in their tanks when they go underwater. They have liquid oxygen. Yeah. It is gas at room temperature and 1 atmospheric pressure. But if we take that gas and we compress it, we can turn it into a liquid.
So they're making oxygen?
You guys know this. You've seen the the cans of CO2.
You fit more if
You've seen the cans of CO2.
I didn't know how that.
I thought it was
Yeah,
just air.
yeah, you didn't know how. It's not air in a can. The air, you ever shake it?
No,
It's a liquid.
It's a liquid. How's
It's shaking. It sounds like a liquid.
Can't it fit more if it's a liquid instead of a gas?
Yeah.
You can freeze things off with it because it gets real cold when it expands.
So oxygen can be liquid.
Yeah. So can carbon dioxide. That's what a lot of that CO2 in a can. That's what we use. Yeah, question.
Like a spray?
Yeah.
Can you turn it to a solid? Yes,
Yes.
absolutely. Why are we putting things away? Why do I hear it clicking around?
So there's a minute.
Oh, we got a minute? You guys said we had time.
We did. 10 minutes ago.
We got 2 minutes.
Yeah.
We get out at 3.
All right, let me finish my statement. No bathroom breaks. End of the day. Let me finish my statement. So yes, you can freeze oxygen. You go into space, you'll find frozen oxygen, frozen methane. It takes a lot of very low temperature to freeze it, but we can. Listen, don't put stuff away. Listen to what I'm saying. You guys have to start learning them not to put things away until the class is over. It's very rude. So, when we're talking about saturated fats, what we're talking about, and I'm going to go ahead and quickly draw this. I'm going to draw the X again. And what happens is, if all the carbons in the chain, if it's a long chain, what is it? Long chain of carbon and hydrogen, what is it?
Non-polar.
Nonpolar, and it's a lipid. So the long chain is nonpolar, but it's also a lipid. All right, that's the definition of lipid. All right?
What's the definition of lipid again?
Long chain of carbon. Now, if all the carbons have hydrogen, we call it saturated. So this is saturated fat.
What you said?
If all the carbons have a hydrogen, we call it saturated fat. If all the carbons don't have a hydrogen, if some of the carbons have a double bond, right? If not all the carbons have all their bonds full of hydrogens. Do you see how these two here, do you see these two carbons right here, these two special carbons? What do you notice about them?
They're red.
They have a double bond. So as soon as you see a double bond, we call that unsaturated. All right, go ahead. Push your chairs up. Please clean up your area. I will be after school tomorrow, but not today. Have a good day. We're pretty clear on what lipids are, right?
Yes.
Lipids are long chains. By the way, did we go over the bell work answers?
Oh.
Number one, which of those are polymers? Glycogen is a polymer. That's true.
Starch.
Starch is a polymer for sure.
And C1.
Cellulose is a polymer. Those three are polymers. Glucose is a monomer. Those are the three. See, I know you all heard glucose. Are you ready?
Oh, which other form are carbohydrates?
So which of the following are carbohydrates? What's the only answer there that's a carbohydrate?
A.
C6H12O6. All carbohydrates have CHO only. So this has a C, there's the H, but then this could be a lot of different elements. So is this a carbohydrate?
Yeah.
No, because there's number one, you don't see any O's. Number two, this could be anything. It could be phosphate, in which case no, because carbohydrates only have CHO. We talked about this being saturated, this being unsaturated. So we talked about carbohydrates and lipids so far, right? All right. Hopefully we get to nucleic acids. We did last block. If not, you'll have to finish it off at home. So proteins. Let's look at proteins. Number one, proteins are polymers. Are lipids polymers? No, they're not polymers. Lipids are just chains of carbon. So polymers, remember, they have to have these units, repeating units. So proteins are polymers. We know that's true. And it says here very clearly that the 20 amino acids are the monomers. So proteins are the polymers. The monomers are the amino acids. Let's take a look at some of the amino acids. Let's take a look at the non-polar amino acids. How many amino acids are there? 20. I just said it. 20. And how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. You agree? So there's 9 amino acids here. So these are the monomers. Notice that not all the monomers look exactly alike, do they? They're slightly different. That's important. You'll find out why later. It's important. So that means I would write that down in a note somewhere in my notes. Not all of the amino acids are the same. They all have different parts. But there are parts that are the same. Can someone identify what those parts are the same? Where they are, what they are? Yeah, go ahead.
Oh, the C where carbon's connected to oxygen.
So right around here is the same with all of these, right? And what's the same in and what else is the same?
The The H3.
The H and then the NH3, right? So that part. Somebody this morning said something very cool. I never heard it before in 20 years of teaching, and they're absolutely right. It's like the arrow. It looks like an arrow. See the arrow? The arrow is what's consistent. It's the same. Do you see the arrow?
Yep.
So if you see an arrow like that, you know it's an amino acid. If it's a bunch of these put together, what do we call it? No, these are monomers. A polymer. What do we call a bunch of amino acids? What do we call a polymer of amino acids? A protein. So we're getting it. So it sounds like there's a lot of work to do before Friday, right? 1 week from today. So these are monomers, and when we're going to put them together in a minute, you'll understand a little better in a second. By the way, what's different among all these? The white box. I heard somebody say the bottom, the white box is correct. So this white box, I'm going to go ahead and put a little red line around it. And can I call this red line, can I call it an R group? So it's just called, like we use X and Y in math, we'll use R for proteins. So we're going to call it an R group. So now let's take a look at the basic amino acid structure. If you can identify that arrow, you're really good. You're going to feel very comfortable, because you have to understand something. You will have to know how to make a protein. You will make it in class. You have to know it. It will be on your end of course exam for you to graduate high school. You must know how to make them. So, that being said, you should know what they look like, right? The amino acids. So C, oh sorry, not C, I don't even know what I'm doing. NH3, right? That's one end, isn't it? The N is connected to a carbon, that's connected to a hydrogen, that's connected to another carbon, that's double bonded to an oxygen, there's a single bond to an oxygen. In this case, it's negative. And then this C, instead of trying to draw one specific amino acid, I'm going to go ahead and put that red line, and I'm going to call it R, and I'm going to give it a number 1. How come I put number 1? How many different ones could it be? 20. It could be. You're right. There are many, many more amino acids, but there's only 20 used in living things, specifically in humans. So 20. So out of these 20 amino acids, we could have 1 here. Now we're going to take this R1 and we're going to put it together with another one of these amino acids. So I'm going to add it to another amino acid, and that amino acid I'm going to add it to, it's going to have an NH3, isn't it? It's going to be connected to a carbon. It's going to be a hydrogen. It's going to be a carbon. It's going to be double bonded to an oxygen, single bonded to an oxygen, negative. And it's going to have what here? The red box, the R group. So again, that's the black is what's found on all of them, and the red is what's different on all the amino acids. So you have R1 and R2, and we'll go ahead and we'll connect them together in a minute. Now when we connect them, there's a whole process that we call dehydration synthesis, but we're not going to talk about that today. I'm trying to keep that off this test. But dehydration synthesis is going to let us do this. NH3, C, and H. There's that R, a C, double bond O. And then this is going to be connected to what?
R1 and R2. I mean R.
No.
R4.
No.
R3.
Nope. It's going to be connected to the nitrogen. So what's happening here, in case you don't see it, is this carbon is going to make a bond to this nitrogen.
Oh.
Okay? That's what's going to happen. And when you do that, of course, this still has a hydrogen on it, right? And then this gets connected over here. This still has a hydrogen on it. This is connected to what? Carbon, and then a hydrogen, and then another carbon, and then a double bond oxygen, single bond oxygen. And then you have your R group, right? So here you have your R1. Here you have your what? R2. Do you see that this is 2 amino acids put together?
Mhm.
So we can see that this is R1, this is 1 amino acid, and then this is another amino acid, and they're put together. And you can do this for a very long chain. You don't have to just do it for all this. What can't you see? You want to look at what? So you can make a real long chain out of these. You don't have to stop with 2. You can make them out of hundreds of them. And you do that all the time. Look at your hair. Your hair is a real long chain. It's actually several strands of really long chains of these amino acids. You can't even see a single amino acid with your bare eyes. But that's how long this chain is. Thousands of amino acids, all tens of thousands, hundreds of thousands of amino acids, one after another, all chained, put together and like a web, almost like a spider's thread. That's a protein. And by the way, the reason that some people have curly hair and other people have straight hair and other people have whatever hair is because it depends on what R group you have and the amino acids and what order they're in. So if you have R1, R2, R3, R4, you might have straight hair. If you have R5, R18, R17, you might have curly hair, etc. Yeah.
So like, can the order change somehow?
It can. It's all based on genetics, on your DNA.
So like,
Yeah.
you know how like some people like they get it like a perm if they change something.
That's a little different. Perms is chemically changing your hair. Hair straighteners, perms, that's all changing the connection between the molecules. That's not really changing. That's not really changing the order of the amino acids. The only way to change the order of the amino acids is to change the genes. That's what genes do. They tell you the order of the amino acids. This is it. This is genetics. This is why you're different from everybody else. This is why identical twins are the same. This is why a rabbit looks different from you, because it's all about the order of the amino acids that they put together. That's it. That's the key. And we'll talk more about that later. I just want you to understand what we're talking about when we start to talk about it. Does that make sense?
Mm-hmm.
All right, so this thing, you see this line here, this thing that connects the 2 amino acids, there's something that connects them, and that's this line right here. You see it, that blue line?
Yeah.
That's called a peptide bond.
It's called
A peptide bond. Peptide bonds hold amino acids together. They're the bond, that's the bond that holds that hair that you have together. They're strong, they're covalent, but they're just called peptide because of specifically what the 2 things are connecting. And so, if I have this long chain, let's assume it's a long chain, it keeps going. Right, so let's say it's somebody's hair, real long piece of hair. And there's all kinds of little amino acids here, hundreds of thousands of amino acids to make this long protein. Do you agree? Do you see that? Okay. What's connecting all those amino acids? Peptide bonds. So can I call this protein a poly, what? It is a polymer, you're right, but specifically a polypeptide. You remember we said polysaccharides for polymer of sugar? Well, polymer of amino acids, we can call them a polypeptide. Why? Because there's many, many peptide bonds holding it all together. Are we good with this? All right, so that's polypeptide. So there could be more than one polypeptide in a protein, but another word for polypeptide is protein. There are some polypeptides, some proteins are just one polypeptide long. All right. And by the way, when we talk about this order, right, when we say look at this order, R1, R2, like amino acid 1, amino acid 2, when we say that, when I tell you that this order is important, I can tell you this. Someone that has sickle cell, it's just one amino acid difference between having sickle cell and having normal hemoglobin. Having a sickle cell, having non-sickle cell. It's one amino, and this long chain of amino acids, just one, makes a difference between someone being sick and someone being not sick. So it's important that you understand that when we talk about the order of these polypeptides, the order of amino acids, that it is very integral to biology, important to biology. The functions of proteins are important. So you see this example here, spider's web. You've seen how long these threads can be, right?
Yeah.
You've seen a spider. I don't know about you, but my wife hates spiders, and I swear that she finds them no matter where we go. And more than one spider has been on a ceiling, like in a big tall room, has let down its thread, and is floating from that. They just hang there. It's one long thread. And do you know that thread, this thing you call a thread, is made of one amino acid, then another one, then another, bless you. It's a protein. It's a long chain of amino acids. It's a long polypeptide. So spider, its web is structural, right? Hair is structural. Nails are structural, right? So proteins they function as structural components of a body. They help a body do its thing. Transport. Proteins also transport. What do proteins transport? Well, hemoglobin, we talked about sickle cell. This is the protein that gets messed up in sickle cell disease. Hemoglobin carries oxygen. When you can't carry oxygen, when you don't have enough oxygen, we call that anemia. When you don't have oxygen, there's not enough oxygen in your blood, we call it anemia. Do you see why we call it sickle cell anemia? Because it's anemia because of the sickle cell. Why is the cell sickled? Because the hemoglobin has one amino acid difference. Why is it anemia? Because it can't carry oxygen as well anymore. So sickle cell anemia is because of transporting oxygen. The proteins are structural. The proteins are transport. The proteins are the reason you move, are the reason your heart beats. Muscles are made of protein. Muscles are made of protein. Muscles are made of proteins. And then antibodies. And when you get sick, when you get a vaccine, your body produces these antibodies that are proteins. And they stick to these creatures, these bacteria, these viruses. They stick to them. And they don't let that thing get out of go anywhere. And then white blood cells, they start to digest those bacteria, those viruses, because antibodies are bound to them. So they're like, these things end up being like little Post-it notes. They get stuck onto your bacteria. Anything that's not you gets an antibody made for it. Your body makes antibodies to just about anything. By the way, when this happens too much, when people are oversensitive, we call them allergies. So your body starts reacting to things that aren't harmful. If your body's overly sensitive, that's called allergies. Regulation is so how these things function, or the word enzymes also should be associated with proteins. Although there is at least one enzyme that's RNA. RNAs can act as enzymes. RNA can act as an enzyme. But proteins generally are what make enzymes. We're not going to talk about enzymes right now. We're going to go on. We're going to talk about the cell, and then we're going to do a whole week on labs with enzymes. I'm going to bring in some cow liver. We're going to chop it up in a big blender. It's going to stink a little bit, and it'll be kind of gross. It'll be fresh. It'll be bloody. So all these kids that like horror movies, you'll have fun.
My mom.
So the rest of us that don't like, because I don't like horror movies, we'll have to deal with it, because it's going to be a very interesting lab. But I want to talk about enzymes separately, if you don't mind. But very important to biology, these enzymes.
Wait, are we talking about?
What? All right. I don't need you to know much about conformation except to know that there's proteins fold. Proteins fold. Fold. So that long chain isn't a long chain, it folds up into a shape. Do you see the shape? And the shape leads to function, doesn't it? So that's it. This is the shape, and you can see the shape. And you can draw the shape with atoms, and you see that the shape is pretty much this, isn't it? I mean, this was a little different because it's space filling, but it looks like a bear to you. It does kind of look like a bear. I was thinking more like woodchuck, but whatever. But it folds up, and it takes on a specific shape that functions a certain way. And we call that shape, we call it a conformation. That's going to be an important word for later. Conformation. It's not going to be on your test, though. Conformation. Oh, you'll see how conformation becomes important. Okay? Oh, holding on. You see the chain's parts? The attractions between what parts? What parts do you think what makes up this protein? Amino acids is correct. So what part of the amino acids are different that would allow for different, the R groups. So it's the different attractions and repulsions between R group and R group. That's what makes this fold up. If they don't like each other, they get spread out further. Remember like dissolves like? If this is nonpolar and this is nonpolar, they hang out together. If this is polar and this is polar, they hang out together. If this is nonpolar and this is not and this is polar, they repel, they move away from each other.
So the opposite of that.
They can be the same or opposite, depends on what it is. So if R1 is, let's go ahead and look at it. If R1 and R2, if R1 is nonpolar and R2 is nonpolar, attract. Right?
Yes.
If R1 is polar and R2 is polar, attract.
No.
Opposites attract in magnets, and you'll see that in a minute. But what did we say about like dissolves like? Like dissolve, they're dissolving each other. They dissolve each other. If we're talking about nonpolar and polar, repel. If one's positive, the other one's positive, they repel. Right? They're both now the charges, same charges repel. If you have one that's positive and one that's negative, they attract. And if you have negative, they repel. Does that make sense?
Yes.
So that's it. Kind of simple idea that we can apply to why this is, and you can tell since there's there's hundreds of amino acids, there's all kinds of shapes you can have. All right, may I go on, please?
Yes.
Nucleic acids,
Yes.
DNA and RNA. Now we're done with proteins. We're moving on to nucleic acids, the last of the four. Thank God.
Yes.
It's 13 after. Do you want to just wait to do this at home? Or do you want me to try to do it now? Okay.
I was gonna say home.
You better pay attention or you're wasting your time. So let's go ahead and call up an existing picture here of what it looks like. Come on. This is the monomer of a nucleotide. It's called this is the monomer of DNA. This is called a nucleotide. And I know it's DNA for DNA. And I know it's DNA, number one, because DNA is up here, see it?
Bless you.
Number 2, there's no oxygen. Missing oxygen. What does DNA stand for? Deoxyribo. This thing here is called a ribose. That's a ribose sugar. So it's a ribose that's missing an oxygen. Deoxyribose. And the whole thing is a nucleic acid. This is the nitrogenous base here. So there's 3 components to this. Here's your nitrogenous base. This is a phosphate. When you think of phosphate, think of this thing here. So that's your phosphate. So those are your 3 parts. But the whole thing is a monomer. This is the monomer. Do you see it? I hope you do, because that's it. That's the monomer. Now here's 2 of them. Remember we did 2 amino acids put together a minute ago? Well, these are the 2 DNAs put together here. The two monomers put together of DNA. This is the beginning of a polymer. This whole thing here is a polymer, right? A DNA molecule is a polymer. So to be clear, when we're talking about this is the monomer. 2 of them, right? But a bunch of them put together, you get a polymer. Well, do you see the connection? Do you see, here's your ribose. Here's your ribose, the phosphate, do you see it? And your nitrogenous base, do you see it there? That's one nucleotide. Here's another nucleotide. You can't see it because it's off screen, but there's your ribose, there's your nucleotide, there's your nitrogenous base, your phosphates down here. So the point is that you get to connect them one after another, after another, after another in this long chain of nucleotides. Each one's different. You see the different one? There's 4 different ones, right? Adenine, thymine, guanine, cytosine. But it's much easier than proteins, aren't they? Proteins are 20. This is only 4. I told you you'd run out of time. We should have waited. All right.
So again, just to be clear, this is a polymer. DNA is a polymer of these units, these monomers called nucleotides. Now, what's confusing here for some kids, and I want to say for people in general, is that this monomer, right, is made of different parts. So you have a sugar, a phosphate, and a nitrogenous base all make up this monomer. But it's not too different from the amino acid. If you remember correctly, the amino acid for proteins, the amino acid is the monomer. And with the amino acid, the basic structure for this monomer is a carbon connected, no, let me redraw that. You have your amine group connected to a carbon that's connected to a hydrogen that's connected to that R group. Remember that R group? It's important. So you know that there's 20 different possible R groups on there. And then you have this C double bond O. And there's another form of it we'll talk about later when we get into protein synthesis. But the bottom line is that this is an amino acid monomer, and this is a DNA monomer. Now, you'll notice that the DNA monomer, the nucleotide, has 3 parts, the phosphate, the sugar, and the nitrogenous base. The amino acid monomer has this R group, which remember can be any one of 20 different side groups, and then it has an amine group and a carboxyl group. So even though this has 3 parts, it looks a lot more complicated because you have rings, and then the nitrogenous bases, there's 4 possible nitrogenous bases. And I think you know that there would be A, T, G, C. Some of you have heard this before. Adenine, thymine, guanine, and cytosine. And by the way, the difference between the 3 is just that this nitrogenous base is different. These 2 parts are the same. This part's different. Just like with the amino acids, this is all the same with amino acids. It's the R group that's different, and so there's 20 different R groups. There's only 4 different nitrogenous bases. So that's going to be very important as you move forward. Now, moving forward, when we're looking at DNA, if we can just take this whole structure here, the ribose, the phosphate, and the nitrogenous base, and we could just make very simple forms and say we make the ribose, you know what, why don't we just keep the ribose a pentagon? And then from that pentagon, we go ahead and put a circle, put a P in it. That's a phosphate. And this is the ribose. You see how I'm simplifying the form. And then sticking out from that is going to be this nitrogenous base. And generally it's a ring. It can be two rings. It can be one ring or two rings. We'll just go ahead and draw something like that. And they're all connected. This is the nitrogenous base, NB. So this is the unit. And of course the details are over here. And you could actually draw it out in even more detail if you'd like. It would be fun, but it would be time consuming. So this is kind of a very simplified form of the nucleotide. And if we think about this nucleotide and we think about it, one being connected to the other, then we can think of these nucleotides as links in a chain, right? So if you think of any chain, each link would be like your monomer. Now, of course, in a chain, the links are physical. In the links in a monomer, they're chemical. If we simplify it even further, and we look at these nitrogenous bases as these links, and let me just go ahead and draw something like this, where they're just all connected to each other in this big chain. And then we draw that chain going on for billions of nucleotides, right? So each of these is a nucleotide. And what am I talking about when I use the word nucleotide? I'm talking about the ribose, the nitrogenous base, and the phosphate together. And as this nucleotide goes on, it forms this very, very long chain, and these nucleotides on the monomers are the links in that chain. Okay, so let's take a look at this picture again, this diagram. And I think we can understand this diagram just a little bit better now. If you see the monomer down here, the three parts of that make one monomer. Here again you have one monomer, then another monomer. And that's what these rods represent. Each one of these is one monomer. So one, another monomer, all the way down, billions of nucleotides long. This is obviously one short little piece. So you got to imagine a very, very super long, tiniest of strings, all wrapped up inside your DNA, or inside your nucleus, this thing we call DNA. Each one of these links is a nucleotide, and each nucleotide has a different nitrogenous base. So it could have adenine, and then thymine, and then guanine or cytosine. And what you have to remember is these four are what make up these nitrogenous bases. So as we move along and we start to decode this DNA, you got to understand the basic format. And one of the things that you should pay attention to is this thing where you have phosphate and then a sugar, ribose, right? Ribose is a sugar. So phosphate, that's this phosphorus with 4 oxygens around it. We call it phosphate. So phosphate, sugar, phosphate, sugar. So we call this the sugar-phosphate backbone because that's what this represents here, this blue ribbon. So as you move forward, you got to think about when you see this ribbon, this backbone, if you will, going around and around in a double helix. We call this an alpha helix. All right, each one of these is an alpha helix, and there's 2 of them. What you have to remember is that you have a phosphate sugar backbone all the way down that DNA molecule. Okay, so I just mentioned that there's 2 that there's two strands here, and that they're attracting each other, and that's what these hydrogen bonds are all about. Let's talk about that structure for just a second. So if you have this phosphate sugar backbone, right, one of them, on one side you have a 3' end, and on the other side you have a 5' end. So just like amino acids, DNA is directional. So, and we'll talk more about that later when we get into DNA replication. But in any case, it's directional. So off of this sugar phosphate backbone, again, sugar phosphate. Off of this sugar phosphate backbone is this nitrogenous base. Here's thymine, it's a single ring. Here's adenine, it's a double ring. Here's guanine, it's a double ring. And here's cytosine, it's a single ring. You see that they're backwards. You see that this one is upside down as compared to this one. So wherever you have a 5' on one, you'll find a 3' on the other. We call that anti-parallel. Anti-parallel. All right, so what you have is you have another strand. Wherever you find one DNA strand, you'll find the other. And we'll talk about how they're made soon enough. Wherever you find a 3' on one, you're going to find a 5' on the other, the opposite, or what we call the complementary strand. So they complement each other. They're not identical, they're complementing each other. So as you come off of here, it turns out this adenine and thymine, let's say this one is adenine, right, and this one over here is thymine. So A and T, they form two hydrogen bonds with each other. That's because these two species, this nitrogen and this oxygen, these two elements, they make polar bonds between the hydrogen that you see here and the oxygen that you see here. There's a pulling between them. That pulling is what we call a hydrogen bond. So this hydrogen bonding is occurring between the two nucleotides. Now remember, the phosphate sugar is along this black line, phosphate sugar. That's this line here. The same thing's going on here. But between the two nitrogenous bases, just as you see here in this drawing, between this nitrogenous base here, adenine, and this nitrogenous base thymine, there are these things called hydrogen bonds that hold them together. And we talked a little bit about hydrogen bonds earlier, and we'll see more of that during our lab this week. So we see A and T, then G and C actually end up making 3 hydrogen bonds with each other. Now, hydrogen bonds are not covalent and they're not ionic. It's an interaction between molecules where the two molecules attract one another. It's what allows water to stick to itself and to other things. It gives water its cohesive and adhesive properties. Well, when you have hydrogen bonds between these two long molecules, and by the way, all of these all have these hydrogen bonds, and which is what happens is that these two molecules, they pull at each other and twist each other. And because they can pull at each other and twist each other, there's a geometry that's defined. And one starts twisting around the other over and over again. Again, anti-parallels. And we call this the alpha helix. The alpha helix. And what that is, and it's a double helix, so that's why we call it a double helix. Why do we call it a double helix? Well, a helix, first of all, is a twist like a staircase. And the reason it's a double helix is because there's 2 of them, one here, another here, 1 and 2. So the double helix. And it's a double alpha helix is what it is. It has to do with the twist and the geometry of it. So they start off as these single strands, here, and once they start to interact with each other, the hydrogen bonds between the nucleotides twist and turn the two molecules together to form one double helix. This, another word which you'll learn, another word for this alpha helix, this double-stranded DNA, is a word that some of you already know, and I'll just write it out here, even though we're not going to talk about it for a little bit. We'll call it a chromosome. Oops. So chromosome. When we talk about chromosomes, what we're talking about is two of these molecules twisted up onto each other in this alpha helix or double helix form, and all these rungs. When we talk about genetic code or we talk about your DNA, what we're talking about is a message that is defined chemically in this A, T, G, C, C, whatever it is. It could be any combination, and everybody has a slightly different one. And when we talk about bananas and humans having similar DNA, 50% similar DNA, what we're talking about is this code. This code that's over 1 billion nucleotides long. 1 billion nucleotides long for one chromosome, let alone all the chromosomes. And so there's these letters, we give them these designations, we say letters, and these letters represent these nitrogenous bases, cytosine, guanine, thymine, adenine, and that's what we find here in these rungs. If this is the phosphate backbone, the sugar phosphate backbone, these are the nitrogenous bases. We call them the rungs of the ladder, right? The rungs of a ladder are the parts where you put your feet and your hands to climb a ladder. Well, that's where these rungs make up are made up by the nitrogenous bases. The sugar phosphate backbone makes the thick line that you see here in the drawing. Okay, so let's move on. So when we're doing DNA replication, we have to make a new copy of it. And as I said earlier, here is an example of the sugar phosphate backbone. This ribbon represents sugar, phosphate, sugar, phosphate, sugar, phosphate, all the way down. The phosphates are what connect all the sugars together. And then off of another part of the sugar, as you saw earlier in the nucleotide, you have the nitrogenous base, A, G, T, T, G, T, T, etc. So the bases do hydrogen bonding between each other. That's what pulls them together. And as you unzip it, open it up, what happens is that you find matching strands, matching pieces that come in and fill in the gap. And that's how you make two new copies of each DNA molecule. We're going to get into that later. There's going to be a whole week on it. But I just want you to understand, I want you to be oriented on what is the DNA molecule. What does it mean when I see this ribbon? What does that ribbon represent? And let's be clear, that's kind of what I'm going to be looking for on the exam, right? So this would be the sugar phosphate backbone, right? So A would be, and if you want something, you're asking yourself, well, what can I do to try to make sure that I understand this? I would sketch this out. I would put a cover or a card over this section here and ask yourself, what is A? A is a sugar phosphate backbone, right? And I would cover up on the other label, and I'd ask myself, what's B? And hopefully you say B is the nitrogenous base, hydrogen bonding with each other. All right, so that's what we're talking about here. Did you really have to understand how we make new DNA or replicate DNA? No, but you should understand that DNA is copied, it is replicated. And we do make new copies, and the new copies are exact copies. And we'll talk more about how we do that later. So that's it for DNA. And just as a summary slide, let's make sure we understand kind of the big ideas here, at least in the latter half of this. And number one is that you have 4 biomolecules. You have carbohydrates, you have proteins, you have lipids, and you have nucleic acids. With carbohydrates, and you can consider this kind of your study guide, right? With carbohydrates, you're talking about things like anything that ends with OSC. The OSes that we talked about a lot were C6H12O6. And that, if you remember, was either glucose, depending on how you put it together, glucose, fructose, or galactose. And we talked about another OS, and we talked about ribose a lot, especially at the end of the video. And ribose is another carbohydrate, another sugar. These are 6 carbon sugars, right? 6 carbon. This one's a 5 carbon sugar. A little bit different. So another thing about carbohydrates is we know that there's monomers. And the monomers can be any one of the monosaccharides. And specifically, we talked about glucose as being kind of one of the more important ones. That all the sugars are important, but if you're going to pick one, glucose would be a real good one to be familiar with. And of course, since you have a monomer, you're going to have polymers as well. And the 3 polymers we talked about were chitin. We talked about another polymer called cellulose. And the last one that we called glycogen. This is humans. This is a tree structure. Energy storage. Chitin is structure for insects, right, or arthropods, actually, not just insects. And we talked about one more, which is starch, which is plant, and I shouldn't have put tree structure, but I should say any plant structure, really. So not tree, not just tree, but plants, all plants. And starch is energy storage. For plants. So we have chitin, we have cellulose, we have glycogen, and we have starch. The 4 polymers you should need to be able to reference and understand. Do you need to be able to identify them? No. Do you need to know that there are 4 polymers that we've talked about in class about carbohydrates? Yes. Do you need to know that monosaccharides are the monomers of carbohydrates? Yes. Do you need to know that C6H12O6 can be glucose, fructose, or galactose? Yes. Do you need to know that ribose is a sugar? Yes. So those are what you need to know. And if you're asked, do carbohydrates make polymers? Sure, that's one of the 4 biomolecules that make polymers. Okay. Proteins, we talked about amino acids. And we looked at the structure. And we said that they have these R groups, and there's 20 different ones, and that they're connected. And we talked about carbon chemistry and how carbon makes its bonds. We know carbon makes 4 bonds. And you can draw it with an H or without an H. I'll go ahead and put it with an H for now. In any case, this is your structure. You know that the whole thing is a monomer. You know that this R group is interchangeable. There's 20 of them. So there's anywhere from 1 to 20 different amino acids that can be found in animals and plants. So that would mean amino acid. And we know we can put them together. If we take one amino acid 1, that's one of these things here, right? Is here, amino acid 1. And we connect it to amino acid 2. And what's the difference between amino acid 1 and amino acid 2? The R group, right? They could be the same amino acid, right? So you could have more. I keep saying that they're different. We have to say that they can be different, but they could also be the same amino acid. So I could say, glycine, and then connected to cysteine, etc., all the way down. And so the chain can have repeats. I don't want you to leave this video thinking, well, there's no repeats in amino acids. They're each different. They can be the same, but the point is that it's the R group that makes it glycine. So each of these is defined as glycine because of that side chain that sticks off it. Why do I say that? Because the very essence of the amino acid, the structure, the basic backbone of the amino acid is the same. That's this blue section here in all amino acids, right? Give or take a hydrogen. So the blue section is the same. It's that R group that's going to be different. That R group can be the same inside the chain, but eventually you're going to run into a different R group as you make different amino acids and different proteins. So a chain of amino acids is called a polypeptide. Why? Because this bond here is called a peptide bond. And again, this chain keeps going on for as long as a protein is. Some proteins are shorter than others, but you get the point. That whether it's short or long, it's one amino acid connected to the other through peptide bonds. I've shown you earlier in the videos what that peptide bond looks like, but that's why we call these long chains polypeptides. And then polypeptides, a protein can be one or more polypeptides. All right. Lipids are just anything with this X structures of all kinds of different kinds of lipids. And then you have this long carbon chain. Usually it's mostly carbon-hydrogen all the way down the chain. And they can be saturated or unsaturated. And you can also, don't forget that, or if you've done your reading, you should know that there's another class of lipids called steroids. So things like cholesterol, things like testosterone and estrogen, they're all lipids. So there's these long chains. A lot of steroids have rings, but in any case, they're long chains of carbons, and mostly carbon and hydrogen. Another thing to remember, by the way, about carbohydrates is that carbohydrates are C, H, and O. All right, that's all there is, C, H, and O. Proteins have an N, an S, a C, H, and O. Right? So those are atoms involved in proteins in general. Lipids are mostly C and H. Now, could they have other elements in there? Sure, but mostly C and H. Sometimes there's obviously a phosphate and etc. But with nucleic acids, the three main elements you're talking about with nucleic acids are nitrogen, oxygen, hydrogen, Carbon, of course. Carbon's going to be the key. Let me just put all the carbons in the kind of this red as being incredibly important. So really what we're talking about carbon, we're talking about carbon chemistry, remember? I hope you remember that. So all the reds, all the carbons are incredibly important here on the C's. It says NC, NOHC, and don't forget phosphorus because of the sugar phosphate backbone. Nucleic acids are made of a backbone of sugar phosphate, and but their monomers are either ribose or deoxyribose. If it's ribose, then we call it RNA. If it's ribose, if it's deoxy, in other words, if this position here has no oxygen, then we call it DNA. So DNA and RNA, those are the big. That's really one of the key differences. There's a few others we'll talk about later. Phosphate, which I'm just going to put as a P with a circle. P with a circle really means phosphorus element connected to 4 oxygens. And remember, these oxygens can each make 2 bonds. So these are how many bonds these make, what charges they have on them, what they're connected to. So that allows this one to connect to something, this one to connect to something else. So that's how phosphate ends up being the connector of all the sugars, the sugar phosphate backbone. And it keeps, so again, it keeps going down on this end to phosphate. And then off of here, you have your nitrogenous base, your NB. That's not nitrogen and then boron. That's nitrogenous base. So this is a variable. And then here, of course, you have ribose. So the nitrogenous base, what possible nitrogenous bases could you have? For DNA, it's going to be A, T, G, and C. One other difference between DNA and RNA is that T doesn't exist in RNA. What you get is A, U, G, C. So the U and the U and the T, the U replaces the T in RNA. Okay, so those are kind of the 4 main biomolecules that we have to talk about. We've talked about carbon chemistry and how that works. We've talked about covalent and ionic bonds. We've talked about polar and nonpolar bonds, like dissolves like. We'll have several labs, or 2 labs this week to discuss all this. I'm going to upload this video. It's going to be very long. I'll make sure to remind you, and I'll remind you now at the end, that this was just meant as a reference. So find the part that you didn't understand, or you need to go back and review based on your assessments throughout the week,